So what I want to do here is go over some of the Chapter 2 homework problems. Hopefully some of these were straightforward and hopefully some of them more challenging too. Um, so I'm going to get rid of the sidebar. Ooh, wow, that's almost too big. At any rate, so for problem number 7, it gave you a graph here, and it was talking about that as a speed, velocity versus time for heart or blood going up through an artery, maybe the aorta. So this book has a lot of medical examples because it's designed for people who might go into medical school. Um, so if we want to find out the displacement, we need the area of this triangle. So there's a couple easier ways to do that. I did that a tough way. I split it into this triangle and this triangle. But in fact, you could split it into the whole triangle. It would still be 1/2 base times height. That gets you an area of 0.08 meters. So remember, the area, or in this course, sometimes the integral, of a velocity versus time graph would give you displacement. For problem number 10, it's actually referring back to the same graph and asking you to determine the acceleration during each region. Well, between 0.1 and after 0.3 seconds, there's no acceleration. Between 0.1 and 0.15, I need to get the slope of this graph, so that's dv dt, or change in velocity over change in time. That's 16 meters per second squared, because that's only 5/100ths of a second. A way you could figure this part out conceptually is if it's taking 3 times the time to go back to 0 meters per second, the magnitude of acceleration would be 1/3 as much, but it's going to be negative. So if I take this number divided by 3, I get this number. It's got to be negative because it's a negative acceleration. Or you could simply do dv dt again. For problem 20, I like this problem. It's actually kind of interesting because you can use symmetry to help you out and help you solve some things. So essentially, it's got something thrown up from ground level at 20 meters per second, and then it goes into a hole 10 meters below that. And it's asking you to find this final velocity. So what you should recognize is that this speed up would equal the same speed downward at that height, because gravity is slowing it down on the way up, and it's speeding it up by this at the same rate on the way back down. So that's kind of the big idea over here. Technically, I guess this should be a delta y, but when I want to find VF, I could use VF squared equals VI squared plus 2a delta y. Well, this 20 meters per second, again, could be positive or negative. It doesn't matter because the whole quantity is squared. And then we've got 2a times 10 meters. And I get that the final speed down here, right when it hits, is 24.4 meters per second. I go back and forth between using 9.8 and 10 meters per second squared. Mainly, it's a little OCD of me if I like to use 9.8 if I know that the answer's not going to be something I can just simply do proportionally in my head. If it is proportional, then I'll use 10. So if it's simple math, I use 10 a lot of times. So to find the time it takes to go up and come back down, we can use the most general definition of acceleration, which is change in velocity over change in time. Technically, this delta should be in front of the t still. Rearrange that. So my final velocity is down at 24.4 meters per second. My initial velocity is up at 20 meters per second. So if I use this formula, I've got to recognize that these signs matter. So anytime you're using kinematics and you have something that changes direction, you've got to be really careful about your positives and negatives. So it doesn't necessarily matter whether you think of up as positive or up as negative, but what matters is that you're consistent about it within the problem. So here I chose down as positive and up as negative, and I was consistent, and so I ended up with a positive 4.5 seconds. For problem 27, it was looking at 3 graphs. Basically, the shape of the graphs all look like that, but initially you had for graph A, it was a position graph, B, a velocity graph, C, an acceleration graph. So the slope of a position graph lets us know the velocity, and at 7 seconds it was this. For graph B, the value of the graph itself determines the velocity, since it would be a velocity graph. So I just looked at 7 seconds and saw what that was, and that would be negative 20 meters per second down here. To find out the velocity at t equals 7 seconds for the acceleration graph, what I have to do is I have to think about the starting velocity, which it told me was 10 meters per second. And then, yeah, it told me it was 10 meters per second. And then I need to look at the area between 0 and 7 seconds. So there's a negative area here. There's a positive area here. Between 3 and 7 seconds, those cancel out. So I'm really only interested in the net area here between 0 and 3 seconds. And you could either do that by counting boxes or using geometry. I ended up counting boxes and recognizing that each box is 10 times 1. So I ended up getting a change in velocity of 65 meters per second, plus my initial velocity that it told me was 10 meters per second. So that's the final velocity of 75 meters per second. 39 would be one that might be easy to get fooled on. These are the graphs. I didn't draw this very well. Curve, straight, curve, straight. These are pretty easy to see. So it's asking you to draw a ramp for like a rock or a marble that was rolling, showing this. Well, I start in a positive position. So that's my 0 position. I start way positive over here. I start with a negative velocity, but it becomes less negative, indicating a positive acceleration, which is also shown down here. So if I'm moving to the left, but I have a positive acceleration, that means my acceleration is to the right. So essentially I'm going up a ramp here, meaning I'm slowing down, moving to the left. In this region it's flat, and in this region it's flat, because there's no change in velocity. This region looks steeper than this one, so therefore I think the ramp is steeper, causing a greater negative acceleration. So I think that would be kind of a reasonable thing to say, and this steeper slope of this agrees with the higher peak of this. Number 49 took a whole page for me. So hopefully you look at the PDF. There's probably a few ways to do this with kinematics. The mass really didn't matter here, by the way. You're accelerating a rocket 30 meters per second squared upward for 30 seconds. Then the fuel runs out, but you're still going to coast upwards. And then you're going to reach a peak and then fall downwards. So I split this into 3 parts. Part 1 when it's accelerating upward, Part 2 when it's accelerating downward but still moving upward, and Part 3 where the rocket's accelerating downward due to gravity. So the first question really was asking you to figure out the maximum height. So to do that, I ended up thinking about Part 1 using this equation, and I got my change in elevation as 13,500 meters if the rocket was accelerating for 30 seconds. I also figured out the final velocity, which was 900 meters per second. I didn't need that to find the maximum height, but I will need it for some other things. Actually, I did need it for the maximum height, sorry. So over here, for Part 2, I know that at the tippy top, the velocity is going to be 0 for the rocket. This original velocity isn't the initial velocity from ground level when it launched, but it's the initial velocity that's the same as the final velocity from Part 1. In other words, it's the speed that the rocket's moving just after the fuel runs out. And that's 900 meters per second squared upward. And then we've got 2a delta y. The acceleration is downward, so that has to have a different sign than the velocity here. And so when I do that, I get this mathematical equation. Move the 810,000 to the other side. They both become negative. The negatives divide out. And I end up getting that this is increasing in height by 40,500 meters in Part 2. So notice, interestingly enough, that the increase in height is much more after the engine's gone off than when the engine was firing. That's because it's moving up very fast here at 900 meters per second at the end of the burn. That's actually like a lot of NASA rockets. You have the fuel burn at the beginning, and then to get into a stable orbit, basically you coast up to that orbit, and that's much more fuel saving. Okay, Part 3 here, I'm looking, actually this is really only useful for figuring out the falling part and the falling time, and I'll get to that. So to answer part A, the maximum height is this height, which is 13,500 meter increase, plus this height, which is a 40,500 meter increase. So that's 54,000 meters if G is 10 meters per second. That's great.
And report it to the gym for script Panther filming by 11 a.m. The quicker you show, the quicker.
And nobody will be there on time.
Grab your colleagues and build your letter.
Fantastic. Anyhow, this is, if I use 9.8 for G, I'd get 54,800 meters, by the way. So, it doesn't matter. Again, the logic's still the same. The numbers are just a little different. For part B, it's asking the total time. Well, this thing is accelerating upwards for 30 seconds, so that's easy. Here, I can go back and I can figure out for the time during the second region, the change in velocity divided by time is interval is acceleration, so I can rearrange that, and it's 90 seconds. Hopefully it makes sense that since the acceleration downward due to gravity is a third of what the acceleration upward was due to the rocket, that it's going to take me 3 times as much time to slow down as it did to speed up. So that's another 90 seconds to get to the tippy top. Now, to figure out the falling time, I can use this general equation. The total amount of this is 54,000 divided by 5. 10,800 equals t squared. So the falling time is around 104 seconds. So the total time this thing is going to be in the air with rockets burning and coasting and falling is 224 seconds. So it asked also to have the velocity time graph. Here the slope upward is 30 meters per second squared. Here the slope downward is a third as much, that's negative 10 meters per second squared. Final velocity as it hits the ground would be negative or downward for 1,040 meters per second. So that's why the rockets have parachutes. Last one, number 57, is actually something I did in class. We went over that in class, so I'm not really going to do that again here. I want you to understand why the acceleration down the ramp is g sine theta. So I showed this for how you get the net force for this object on the hill without friction, and then you use Newton's second law to get the acceleration. That's plugged in here. This delta x can be found by using the trigonometry of this angle in h. The trig sine theta function cancels out in the numerator and denominator. We get the same answer for both. For part B of this, if you plug in specific values, the thing that's fantastic is any values will work to get you this final speed. And notice here, it doesn't matter what angle that the ramp is. All that matters is the height. I do need to put that in meters, though, instead of centimeters to get my final answer, which was that. So hopefully that helps out.